Okay, yes, and my father's from India, so I'm always interested to come here and see this country. So I'm going to talk about work I haven't been doing. This is being done by people in my division, but there has a large overlap with the Whorf model, and those are the parts I'm familiar with in terms of the dynamical core. So I'll be talking more about the parts that are also similar to the Whorf model. So I'll be talking about the MPAS model. This is the model for prediction across scales. The equations, numerical techniques, the grid structure, time-stepping, convection, vertical coordinate, and showing some results we just got at very high resolution, 3 kilometer global, if time permits. And so this is the basic idea of MPAS. It's a shared effort between NCAR and Los Alamos, where Todd Ringler is from. And Bill Skamrock is the lead at NCAR on the NCAR side. And there's an ocean component, which Todd's going to talk about more, and I'll be talking about the atmospheric component here. There are other components too. But the thing they share is the grid structure. They use these called centroidal Voronoi hexagonal meshes, using C-grid staggering and selective grid refinement. I'll mention a little more about that as we go into the talk, but I'll leave most of the grid structure details to Todd in his later talks. Basically, it's an unstructured spherical centroidal Voronoi mesh, mostly hexagons. If you're doing a uniform distribution on a sphere, it's mostly hexagons and some pentagons, and you'd get, for the more general case where you might be doing local refinement, you may get other shapes of cells too. The lines connecting the cell centers intersect the cells at right angles. This is the structure of the grid here. Basically, these cell centers, like B and C, they're intersected by a line at right angles at the cell edge. The velocities are defined only at the cell edges as a normal velocity. You can generate meshes based on a density function, how fine you want your grid anywhere in on the globe, and then it has to mathematically produce the grid that obeys these properties. It's a C grid, so the velocities are solved on the faces, and the only places the velocities are defined are normal to the faces. This is what you need for the fluxes across the faces. We have a hydrostatic solver, but mostly we're going to be talking here about the non-hydrostatic solver, which is more general. And but the integration schemes are similar to Whorf. So in terms of how you deal with the sound waves and the time splitting, etc. This is a basic summary in one slide of the main dynamical equations. The variables we deal with are what we call coupled variables, where we use capital letters, and it really just means the density times the normal variable. So the prediction equations are usually in terms of these coupled variables, density times. Then there's a vertical coordinate I'll talk a little about later, which is a generalized height coordinate, terrain following height coordinate, with some modifications, more recent ones from Joe Clamp. Prognostic equations are for the horizontal velocity, and again, like I said, the velocities are very special in this compared to normal grid models, because you can't define a coordinate axis, so you don't do U and V components of velocity, you just have one velocity at each face, and they're all almost independent of each other computations. So it's not a grid velocity, it's just a local velocity, this horizontal one, and then there's special ways of doing the terms for this, which include the kinetic energy, for example, and the vertical vorticity. And then the vertical momentum equation looks more normal. You also notice here we have the Coriolis is actually partly in this eta, which is the global absolute vorticity, and then there's a horizontal. The other component of the Coriolis is the cosine component, which maximizes at the equator and is an interaction of the vertical velocity and the zonal wind. Usually you have to neglect that in hydrostatic models, but in a non-hydrostatic model you can have that. So this is the cosine terms here you see with the E, that's the other component of the Coriolis force. Then there's curvature terms. Just in this case, the curvature terms only relate to the curvature of the Earth. On other grid models, you'd have curvature related to the lateral curvature of the grid lines, but in this case, the only curvature you're dealing with is the curvature of the Earth. So that's the ones with the R in them. These are curvature terms. And then we also have a potential temperature equation here, density prediction equation, and other scalars which are typically moisture and a few more variables. And all of these are written in flux form. I'll mention that a little later. Then we have diagnostic relations. The theta m I've mentioned here is not really theta alone. It's a combination of theta and QV, which is more useful when you're computing a pressure. So the pressure is diagnostic, and it is basically proportional to theta n to the power gamma. And so we don't have a prognostic pressure equation. We're basically, it's almost part of the theta equation, is what the pressure is. And then you have the density here, which is just a definition of the moist density is the dry, divided by the dry density is just 1 plus these mixing ratios. More details are in this paper here, just published in the Monthly Weather Review. Now these are non-hydrostatic equations. So what is meant by non-hydrostatic equations? It means we use the full vertical moment equation with the prognostic equation for W. Accurate defined scales, that means the grid size, the length scales horizontally and vertically, if they're comparable, that's a non-hydrostatic flow, and you need non-hydrostatic equations to solve any system like this, and this would include thunderstorms or flow over small terrain features. You can only do them accurately if you have a fully non-hydrostatic model. The hydrostatic approximation would limit applications to where the horizontal grid scale, the horizontal length scales are much larger than the vertical length scales of the things you're dealing with. So synoptic weather systems, more synoptic scale models are usually hydrostatic, but when you get to the more cloud scale models like this one and WRF, you have to have a non-hydrostatic set of equations. They're also compressible. So we're dealing with the full mass continuity prognostic equation for density. In other non-hydrostatic models, pressure is often the prognostic variable, which I mentioned. We here use rho theta, and theta is the equation that actually carries, rho theta is the pressure in a sense. So we don't need a separate pressure equation, but we do have a density equation. So it being compressible means you allow sound waves which have speeds of about 330 meters a second. These are meteorologically unimportant sound waves. They're just there because they have some numerical advantages of solving them. The numerical advantage is it keeps the computations local, in contrast to inelastic sound wave filtered equations that require a global Poisson type pressure solver. So by keeping the computations local, that helps multiprocessor parallel computers because you're not doing a lot of communication to solve for the next time step. You only need information from the neighboring grid cells to compute your next time step. There's a disadvantage, which you have these fast waves that you have to deal with, and they need shorter time steps. So we have to find a way to deal with those. This is basically following what's done in WRF, and there's a paper on the WRF numerical methods by Clem Skamrock and myself. So we use time splitting. Fast terms can be separated, and dynamical variables updated with these variables on a short substep, or which is also known as the sound wave or acoustic step. The fast terms are the velocity pressure interactions and the velocity density interactions. So only a few of those terms in those equations I showed are really fast terms. There are slow terms, which are typically convection, buoyancy, Coriolis diffusion, pressure gradient, the large scale part of the pressure gradient, and the physics. Those are slow terms. You don't have to compute them so frequently to update them. So there's certain things you have to compute frequently on a shorter step, and that's what we mean by time splitting. So we use semi-implicit time splitting. Explicit sound wave splitting gives a reasonable time step for horizontally propagating sound waves, typically 4 to 6 sound short steps per advection limited long step. So the long step is limited by the advective speeds, jet speed, for example. The vertical motion is more often a limit for the long step, or as you get to finer scales at least. So this is in contrast to horizontally implicit sound scheme, which requires a global Helmholtz pressure solution. So we're using an explicit horizontal sound wave solution that requires these short split steps, 4 to 6 typically per advection step. However, the smaller vertical grid size would limit the time step for vertically propagating sound waves too much. You can't do the same thing in the vertical direction. So the vertically implicit method is used for interaction between W and pressure, the vertical momentum and pressure. Remember, it's the pressure momentum interactions that allow for sound waves. So we make this vertically implicit, and that involves a column tridiagonal matrix inversion. So it's a simple solution in the vertical column done all at once, allows you to do vertically implicit sound waves. So the scheme is therefore horizontally explicit, vertically implicit, and makes it quite efficient. And it's only dependent on the horizontal bit size, the number of short time steps. We also use third order Lundy cutter time step. The aim is to evaluate the main dynamics terms at the center of the forward step. I'll show a diagram later that illustrates what I mean by that. But so advection, buoyancy, coriolis, and pressure gradient are the main dynamics terms. We use two intermediate predictor steps to allow this to get to the center of the forward step. The time-centered values are then used for the final step. And the advection of all the non-dynamic scalars also follow this method in terms of you're doing a prediction and then you're doing the final advection using the time-centered value of the advection term. Physics tendencies, for example, any kind of heating and diffusion are evaluated only at the beginning and are just forward steps. So this is a diagram which shows what the Lundy cutter looks like. You do the physics tendencies first, then you go into the first case advection, you go to a third of a time step, and get a new advection term which can then be advanced from the beginning to the half time step. Then you compute the final advection using the half time step values, and that's used as you finally do the full step from the beginning to the end using this advection, which is centered now, and that makes it more accurate, and that's why it's third order accurate. And during this, you're also doing these small steps I was talking about before for the sound waves. So it's two types of splitting going on. There's the Lundy cutter splitting where you're doing the advection several times, and then you have these pressure velocity interactions which force you to do some terms on these smaller steps. And then at the end, we tend to do the microphysics as a final physics adjustment process at the end of the time step. So now we'll go a little more onto the advection. So at high resolution, we're dealing with bit sizes of less than 10 kilometers, and we may have the order 10 scalars. For climate, there may be about 30 scalars, and you're dealing with aerosol and trace gases. Chemistry, you could have 100 scalars. So scalar transport can be quite a large part of the cost of the model. And the overall solution accuracy is also dependent on the accuracy of scalar transport. So there's some motivation to using higher order scalar advections. The horizontal velocities, like I mentioned, use a C-grid staggering, meaning the normal velocity is only defined and stored at the cell edges, as here. And in an unstructured mesh, this only has a local direction, as there is no global grid direction, like I mentioned. So it's a little unusual if you're used to thinking of grids and velocities along grid lines. The x and y velocity, that concept doesn't exist here anymore. So in terrain following coordinates, the fluxes use a coordinate vertical velocity to allow you to put them into this kind of a simplified flux form. So it's only really the horizontal parts and the vertical part which uses omega, and omega is just v dot del zeta, zeta being the coordinate value, and it turns out that, and this should say, omega is diagnosed from prognostic Cartesian velocity variables vh and w, and becomes w when the coordinate is flat. For example, over oceans where zeta also becomes z. So this becomes just a w and a z when the coordinate is flat, and it's modified with u and v, and the metrics related to zeta variations for sloped coordinate surfaces. So the slope effects are accounted for by using this omega term for the advection, and it simplifies the form of the advection equation. So this again is a Lundy cutter method, and in what we have to do here, so each time you do the new advection computation, and that's what this L is. But then to update the variable, you're finally summing over all the faces to give you the new value. So these are the fluxes at each of the edges, the e's of the edges here. And you're summing over the edges to give you the flux, the new value at the next time step. So that's basically what this says here. So considering first what the Lundy transport here, you have to compute the flux at I. You use I plus a half and I minus a half. These are the grid cells on either side of the grid box I. And each of these fluxes is a velocity at that face point, which the velocities, remember, are staggered, half a grid cell in the C grid staggering, so the velocity is at that point, and then you have to average the scalar to that point. That's what this is. When you go to third and fourth order, which is what we prefer to do, this is a simple second order representation. We prefer to go to third and fourth order. Then you have, in addition to the term here, you have another one which depends on the second derivative of your scalar. And then for third order, you may include another term here, which would be also dependent on the sign of the velocity, being more of an upstream approach. So this is a second derivative and linear in a very simple one-dimensional sense. It's just the 1 minus 2, 1 combination of variables in the neighboring grid boxes. But when you go to this more general mesh, it's not so easy. So the second derivative can be expressed like this. It's a d2 psi by dx squared. So when you're trying to do this on the MPAS mesh, you have to represent these terms to get up to third and fourth order, in addition to your standard second order term. And what you do for these terms is to try and approximate them with a least squares fit polynomial to compute the second derivative. So at the edge E1, for example, where you're doing a flux, you need a second derivative at the cell centers C0 and C1. The least squared polynomial fit for C0 uses values at cell centers C0 through C6. These are the surrounding ones, plus itself. So you make a polynomial from these 7 points in this case, and you get a polynomial, you get the value of the gradient and the second derivative at this point, and you want the second derivative in the direction towards the edge. So having got a polynomial fit from these points, and it's a second order polynomial, you can then compute the second derivative at each of those points, which is what you needed to get the higher order advection. So these polynomials give second derivatives in the direction C0 to C1 that are used for the edge E1. And by storing coefficients, you can pre-calculate a lot of the coefficients to compute these very efficiently during the run, just using the values around the points as inputs. And more details are in the Skamrock and Gassman paper. This shows just the benefits of using a higher order. There are actually 2 different models here, but the MPAS is in red. And this is a test case where you try to evaluate the accuracy of the model and how it degrades with time. And this is a simulation up to 10 days, showing that the third order accuracy is higher than the second order accuracy. And you get that benefit by having this second order derivative in the advection terms. Next, I'll talk about the plane following coordinate, the vertical coordinate, which is something developed by Joe Klempedenker. And this is the unique thing about this coordinate is for complex terrain, represented here, the coordinate actually smooths as you go higher up. For normal sigma type coordinates or zeta coordinates, you would see, even at small amplitude, you'd see the same wavelengths at this level. So the idea of this coordinate is to try to remove the short wavelengths as you get higher up, because there's no need to have them. Joe Klemp has come up with a method of doing that, which works very well and actually has some benefits. First, I'll talk about why pressure versus a height coordinate. In WRF, we've actually got a pressure vertical coordinate, whereas for MPAS, they're going back to a height coordinate. The original WRF in early 2000s had a height coordinate, and then we switched to pressure coordinate later. But now, for MPAS, they want to go back to the height coordinate again, because in some ways it's simpler. So for the pressure or hydrostatic pressure coordinate, it's a historical choice for global and regional hydrostatic models that allows the atmosphere to expand vertically. The top surface in the pressure coordinate is actually our pressure surface, which is more natural in the sense you can expand. When you heat, for example, when you heat the column, it can expand upwards. If you put that top surface far enough away, those issues become less important. So the idea is, by going to a high coordinate, if the top's high enough, you can avoid the problems of having a lid at the top. So in the pressure coordinate, the top is a pressure surface, whereas in the high coordinate, the top is basically a lid. W is 0. The other advantage of a pressure coordinate is non-hydrostatic terms are readily isolated, and it's easy to do a hydrostatic switch. It's harder to do that in the high coordinate. Non-stationary coordinate surfaces, however, require time-dependent terrain metrics. There's some computations you have to do every time step because the coordinate surfaces are moving in a pressure coordinate. And the removal of reference sounding from equations is more complicated. You have to define basically a pseudo-sounding everywhere, and that is defined as your reference state. Whereas in height, which is now used for MPAS and was used for the previous older version of WRF, this is the historical choice for non-hydrostatic or cloud resolving models. M5 also had a similar coordinate to height. Typically employed with rigid upper surface or constant volume. The stationary coordinate surfaces allow more flexibility in accommodating terrain. And this is part of Tibetan's vertical coordinate modification. It can only be done with a high coordinate because of these stationary coordinate surfaces. And having the metrics constant with time also means you don't have to recompute things like the level thicknesses every time step because they stay fixed. So this is a summary of where Clem's new coordinate fits in. The basic terrain following coordinate is expressed like this with the terrain height here, and it basically goes from terrain following to flat at the top. There's also a hybrid terrain following coordinate which can go to flat at other levels. The terrain influences are removed faster than linearly with weight. When you go to, you can use different formulations for this A of zeta. That's a more generalized version. Which removes errors in computing horizontal gradients at upper levels. You'd like the coordinate surfaces to be flat at high levels because it'll distort your upper level features less by having a flat coordinate surface. And so influences of all terrain scales are removed at the same rate, typically in these coordinates, and the potential for low level pressure gradient errors remains, however, because you still have these steep slopes in your coordinates at low levels. The new smooth hybrid terrain following coordinate that Joe Clem has developed for MPAS now uses an HS, a smooth terrain, instead of the full terrain, and that's something that varies with height. So the basic terrain following coordinate HS becomes H. In the hybrid terrain following coordinate, let's see. So in the pure height coordinate, A of zeta goes to 0, and it just becomes Z equals zeta. But he's chosen A zeta goes as a cosine function, which looks like this. And the HS is smooth. This is a smoothing operator as you go from n to n minus 1. These are levels going upwards. And you finally get to this isn't the top of the model. Well, actually it is. But this part of the term, the HS part, is a lot smoother by the time we get to the top. But at the same time, we're also doing this term, which is flattening the coordinate surface to more horizontal. So it's a combination of these two effects that is going into your new vertical coordinate. And you can actually find more detail about this in Clem's recent MWR paper. This is some tests on this coordinate with idealized terrain. This is an idealized terrain with 3 hills or 4 or 5 hills. defined by this function. And basically you start with a initial potential temperature field that's flat and no wind, so nothing should happen. You also put a stable layer in here with n equals 0.02, which is even more of a challenge because then you have a vertical gradient of a change in the vertical gradient theta. The constant vertical theta gradient actually gives you less problems than if you have a change in the vertical gradient theta because of the way the slope terms are handled. So this is an even stronger challenge to the slope coordinate surface. Because remember, the coordinate surface is going to slope in here as well. So this is showing three examples: the basic terrain following coordinate, the hybrid terrain following coordinate, which keeps the terrain elements higher up, but stops at some level here, and then the smooth hybrid one, which is a little smoother, you can tell, than this one, in terms of the coordinate surfaces as you go higher up. And this shows the potential temperature. Again, there should be no change because, numerically there is noise generated because you have sloped surfaces. You're trying to represent a horizontal pressure gradient on a sloped surface, and you can't do that very accurately, especially when you have strong stability layers and changing stability with height. So these are due to inaccuracies in trying to represent a horizontal pressure gradient, which is what you need for the U-wind component on a sloped surface. And by smoothing the coordinate more, and making it more horizontal quickly, and also making the scales longer, you actually improve that situation quite a lot. So now you can get much more accurate horizontal pressure gradients more close to the surface. And this is another with more complicated terrain, and again it shows the same basic results, but again you're getting a much more improved theta variation with the new coordinate. And again, and down the maximum vertical velocity, you also see that the vertical velocity is also being kept low. Again, that should also stay zero in the ideal case. So this noise is related to this noise in the theta field. So these are all resting atmosphere situations which really challenge the coordinates. I would note also that if there is any slight weak flow, a lot of this noise goes away anyway, because there's an advection time scale. This takes a long time to grow. So the advection time scale can dominate that and prevent these things from growing. So this is just the strongest possible challenge by having things stationary to do this test. And here's one with MPAS itself. This is now the global grid, using 120 kilometer grid size and 40 levels, up to 30 kilometers, and but an idealized sounding, which is basically stable, different levels of stability in a step function. And here is the Tibetan plateau, which of course is the biggest challenge in the global area. And so this is a cross-section through it with the basic terrain following coordinate and the smooth hybrid coordinate, which is much smoother here. And this is a blown up view of the same thing. You can see that it's going to be much smaller slopes here, which should improve things. And this is the potential temperature perturbation at 3 days with, again, stationary initial conditions. So again, it's a reduced error. Anything you see here is an error because there shouldn't be a perturbation in a stationary atmosphere. So this has helped a lot, even over the Tibetan plateau. And the vertical velocity as well here. The only errors you do see are right near the surface, where you do still have the strong slopes. You can't really do much about that. Although Jokon does have some ideas on how to deal with the pressure gradient there too. But that's not in this talk. So, and then also running MPAS with real weather, and looking at the Andes, which is another challenging area. So this is South America, the Andes Mountains. And again, over a cross-section through here, you see the difference in the coordinates. And you can see this pattern is a little more realistic to a dynamicist who knows what mountain waves would look like Joe Clem you definitely would prefer to see the mountain waves look like this compared to this. So it does seem like it's giving you a cleaner solution in this situation as well, with real data. And that's the vertical velocity, so these are just the mountain force gravity waves. This is stationary set of gravity waves. So the height-based terrain following vertical coordinate is implemented in MPAS with flexibility, efficiency, and simplicity. The terrain following vertical coordinate with terrain following vertical coordinate with smooth coordinate surfaces allows the influence of smaller scale terrain features to be removed more rapidly with height. Note that pressure-based coordinates, such as in WRF, are not amenable to this kind of coordinate smoothing. So this was one of the advantages of going back to the height coordinate, to be able to do this kind of thing with the coordinate. Now I'll show some results from MPAS. We have now physics in this model, some options even. So there's microphysics, there's a couple of cumulus parameterizations, surface layer scheme coupled to the land surface, the NOAA land surface, the YSU Yonsei University planetary boundary layer scheme, and RTMG or CAM radiation. And this is how MPAS can be used to refine regional refinement. So this, for example, is a grid, and the grid cells are shown much bigger here than they really are, just so you can see them. MPAS is 4 times finer, even at the, so it goes from a 60 kilometer mesh to a 15 kilometer mesh. But what you see here is 4 times bigger, so it's 240 to 60. But this, the region of refinement is here, over the East Pacific. And this is just a snapshot of results. This shows the analysis. This is what they call a atmospheric river. It's water vapor flow. And this is accumulated precipitation maps. So what you have is this is the uniform resolution run, and this is the where you have high resolution in this area. You can see in the areas where the resolution is the same, the solution isn't changing much, but in this area there is some slight extra detail that you can just about make out here due to the high resolution, but there's no problems, it seems, as you go from one resolution to another. In this, it's basically a smooth transition from one resolution to another. And that's the idea of MPAS, is rather than go to M-Nifty, which has a very sharp transition from one resolution to another, you have this more smooth refinement going on, which gives you a smooth, no obvious boundaries in your solution. And this is just another example from the same run. And this is the vorticity, which should show noise even more clearly. And again, here you see the original uniform mesh and the refined mesh. There's some more detail in the vorticity structures, but you don't really see where the boundary would be. It's somewhere, it's gradually transitioning resolution from here to here. Now we go to the, they've just recently had access to a high-power computer at NCAR, where they can do 3-kilometer global simulations. So they've done a couple already. And this was the first one in 2010, October, where there's a tropical cyclone in Chaba. There was another extratropical cyclone with the lowest recorded surface pressure in North America, and then there were isolated tornadic storms observed in the warm sector ahead of the cold front. I'll show a couple of things from blown up images from these two. This is the convection over the US. This is the US here, and you see the front. This is actually expressed in terms of reflectivity, dBz, but it's taken the microphysical fields to compute that. So you see the front here. This is the theta at the first level. The cold air is back here. The actual convective outflows, you can see individual convective outflows here, slightly cooler air, basically downdrafts. And these are the upper level 200 hectopascal vertical velocity showing individual cells, and some of these are splitting cells. So in a the global simulation, they have successfully attained splitting thunderstorms at 3 kilometer grid size. And you can imagine there's so much to look at on the global grid that they're pretty excited by all these results. Yes. This was, the 3 kilometer was a completely globally 3 kilometers, which is, I have the number of grid points in there. The number of grid columns is something like 65 million. Well, here is globally, this one is completely 3 kilometers globally. So you would also have this resolution over India. This is Typhoon Chaba in the Pacific. Again, we're getting a very realistic looking reflectivity signal for the, and this is the 6-hour precipitation for this typhoon. So you are resolving the core of these convective systems. Let's see if this works. All right. And this is a simulated OLR, the outgoing long-wave radiation. For that same case, I think you actually see each other. Chaba's over here in this area. And so you're getting realistic looking cirrus clouds, and there's so many things you can look at here that it's almost too much information. I'll go to the second case, which was they chose this. Let's see, this is still the first case. We also had Tropical Cyclone Richard in this case, which became a hurricane. And again, that's another realistic looking core. This is actually the Yucatan Peninsula here, so Mexico is over in this direction, and this was just making landfall in Central America. And this is the rainfall pattern associated with that. And this is actually some tests with the parameterizations. We have a 7.5 kilometer run and a 3 kilometer run. 2 7.5 kilometer runs, one with a convective parameterization, KF here, one without, and a 15 kilometer run. So the two with the convective scheme, 15 and 7.5, give very similar results. When you turn off the convective scheme, you start to have a different looking result. But then when you get to 3 kilometers, you start to get some of this convection back again. So there's what we call a gray zone, where you're not quite completely sure whether you should use convection or a convective scheme or not. But when you get to 3 kilometers, you're starting to get back things that you probably would want to see. You don't need a convective scheme anymore at 3 kilometers. So that's the point of that slide. And this shows the precipitation rate globally. And it's a diurnal cycle because there's some continental area that's dominating the global total precipitation. And this shows the 60 and the 15 kilometer runs are basically on top of each other. They're the green and blue lines. And then the 3 kilometer run is a bit of a smoothed version of the same kind of behavior, but giving the same general precipitation over the 5 days it would run. You can see that the 3 kilometer run, since it doesn't have a convective scheme, has a spin up time where the precipitation takes a while to reach this steady level, whereas when you have a convective scheme, it pretty much reaches it very quickly. So there is some delay related to, at least I think it's tropical convection. It takes a while for that to spin up. And this shows the 5-day time average, frequency of the precipitation in each bin. So this is heavy bins of precip on the right here and low precip on the left, and how often they occur. So on the 60 kilometer run, which is red, there's less bins, so it's a little more noisy. But as you go to 7, there's a little more in the high precipitation bins, and then when you get to 3 kilometers, there's a lot more precipitation in the high precipitation bins and less in the low bins. So it's changing the distribution in some way as you go from 6D to 3. It's still being evaluated. This is the second case, which is chosen because of some interesting, you can see America's in here. This is the Atlantic, where there were 3 hurricanes, Danielle, Earl, and Fiona. There's an East Pacific dissipating storm called Frank. The West Pacific had Kompasu. I was actually in Jeju for a workshop at that time, and Kompasu went by, so I remember that one quite well. And there was less success with getting some of these other storms that were in that area, Pacific area. But we did capture these. Hopefully there's another animation that will show that. Let's see. So this is Danielle. That was Danielle. And then you have the next one coming up here, and then the third one's here. So again, you're getting the full 3 kilometer resolution of hurricanes, and we've found from other experience that 3 kilometers does capture the central pressure pretty well for hurricanes when we use WRF. So it's pretty well resolved. You can get the eye and all the dynamics associated with that 3 kilometers. Yes, 3 kilometers, the point of going to 3 kilometers is to avoid having to deal with the convective parameterization. There are some cases where you may still need it, but certainly strongly forced systems like the supercells and the hurricanes, you can do convection quite well at 3 kilometers because you're resolving the main parts of vertical motion with the dynamics. And this shows just a numerical thing, that it scales well. This is our new computer, the Yellowstone, and the older computer, 2 different types of compilers. But basically it's scaling well on both. And this just shows that the efficiency stays pretty high even when you have less cells per task, like in this case 640, you're still getting 90% efficiency. So it's basically it's designed to scale well, and it seems to be living up to that. We have the 3 kilometer runs I showed, they actually used, I think, 16,000 processors for those runs. Okay, summary. So this is MPAS. It's a new global atmospheric model suitable for multi-scale research. The global grid enables efficient computations at near uniform resolution. Adaptive refinement is possible with the generalized mesh definition, making it possible to focus on regions. Non-hydrostatic compressible equations on a sphere can handle cloud-permitting resolutions, showing individual convective storms. And there is a plan to make this model available to the general community this year. There'll be limited support at first because it's still experimental. But I think people will be interested in running a global model, and so this is an option for them, hopefully later this year. Okay.
Okay, there's some time for questions.
There appears to be some shift from spectral to finite volume or finite difference because of the boundary condition. Can you elaborate on that? Shift from spectral to finite volume or finite difference for weather predictions or climate modeling?
Well, I'm not involved much with spectral models myself, and they've always been used globally. But we've come from the cloud modeling side, where they've always been using grid point models and expanded up to global. So Clem and Skamrock, who led this effort, they started off as cloud modelers, and they're always used to grid point models. So this is how MPAS developed. It's basically the history of the people who are developing it, more than any kind of change of method by anyone.
I was wondering if 3 kilometer resolution model which you have without convective parameterization, could you compare them with this effort to introduce something called super parameterization in terms of computing effort, in terms of results that you have?
So superparameterization is where you are basically running a cloud model within a lower resolution model at every grid point. Whereas this is more fully integrated because it really is the model, the full model at high resolution. So it's like in some way a step ahead of, well, a step more than superparameterization is designed to be a cheap way of doing basically this. But it does take a shortcut, which is by having a very simple model of each grid cell. It's very simple cloud models. And it doesn't fully interact with the neighboring cells. So this is the next. Yes.
But what about the results? Do you have specific comments on the results that you might get?
I think the superparameterization is it's cheaper but more limited because of the dynamics, how it can feed back from the high resolution model to the low resolution model. So we haven't done obviously any comparison, but they are aiming at two different things. Here we're trying to do a cloud model.
So what computing platforms do you use for this?
Sorry?
What computer do you use?
Yellowstone, Rich Lock can tell you exactly what that is. What is that? It's a Linux.
Yeah, Yellowstone is 1.5 petaflop IBM iDataplex system with the Intel Sandy Bridge processor and MDR14 in
Oh, it's in the top.
it. 1.5 petaflops. Yeah, with all due respect, we like to think that it's big.
So,
It's number 13 in the world as of
70,000 processors or something.
Yeah, 72,288 processors.
Although you can't use them all easily.
So,
It's regarding 3 kilometer time step. What is the time step for 3 kilometer?
Kilometers. Typically, I wasn't able to find that information because I knew somebody would ask. But I think it's around 20 seconds, similar to WARF would use. They can actually use slightly longer time steps with this hexagonal grid than with the rectangular grid they found. So, but it will be about 20 seconds for a 3 kilometer grid because it's still like explicit.
Yeah, I think a really important characteristic of MPAS is a variable resolution mesh. And so a striking difference between when you compare your 15 with 60 kilometer, could you go back to that one? A striking difference between the two is, again, let's go back more, yeah. 16 and 15. Next. Yeah, no, go
This
back.
one.
Yeah, this one. I think this, I'm always curious about the lower panel, which is a variable mesh, has much stronger negative vorticity, at least resolution. So I'm just wondering, have you compared 30 kilometer, just straight, 15 kilometers straight, without mesh, without the standard grid, just like you do for 3 kilometers,
I think
to see whether this is real or not.
So you think it might be related to the mesh refinement?
Yeah, that is the
I
price.
think they have those results, but I don't think we've looked at that. That's
Okay.
a good question to ask them. They have different resolution meshes for this run, and so they would have that result.
Right. And do you still have this?
But I think this is also the negative vorticity. That's also associated with convective areas, and maybe the convection is stronger.
It's also a way you change mesh.
what kind of diffusion you're using for the point?
Okay, there was something there on background. There's a small background value, but and it's done as a del 4 type of diffusive term.
If you use a del 4 diffusion, the computational halo region you are using should be 4 cell wide instead of 2 cell.
Yeah, it depends how you define del 4 for that grid. And,
in that case, it can impede the parallel efficiency further.
yeah, I think they expect to have, well, I don't know how far out they have to go with their halo, but I think there was a diagram which I think illustrated that the halo is at least 2 points away from the central. But that might be an illustration, or I'm not sure how I can trust that. But that's, maybe Con knows the answer to that.
Okay, thank you.
Sir, you have showed the 3 kilometer simulation for thunderstorm. For the same case today, you have done WRF also. So, any improvement you have seen if you compare the results?
We haven't done a direct comparison in that case. We've done comparisons of idealized thunderstorms. We can get almost identical results with the. So in MPAS, you can have an idealized case with a hexagonal grid locally. So you're only dealing with that area. And compare that with the WRF square grid. And they've shown that the supercell case, which is one of the WRF idealized cases, looks pretty much the same on both grids.
Because MPAS, most of the things are like WRF, but it is not sophisticated. So if we see the simulation, what is the difference? Means any difference you have seen like that?
Yeah, the only differences you see are slight differences in the timing. It can use a longer time step with MPAS, but the actual solutions are very similar. So numerically, because they're using very similar numerical techniques, and you can make them use the same physics. So the differences are all related to the numerical grid and Z small.
One more question, sir. You have included that sound waves for this thing. Sound waves.
Sound waves, yes.
So, what is the significance, sir?
What is what?
Generally, we will not include sound waves. But this MPAS thing included sound waves.
The main purpose of including them is just the numerical advantage of keeping the computations local. Sound waves themselves don't do anything meteorologically. They're compression waves. They don't have influence on precipitation or anything like that. So they're only there to allow the, for example, if you're heating this expansion, that expansion is really sound waves, which does that. But, so the model actually represents the velocities that go into that expansion. But those velocities are very small. But it allows you to keep the computations local. Because a sound wave is a local, you only need to know the pressure gradient at one point around the velocity field. You don't need to know the pressure everywhere else to compute the next time step. So it's just a tool to keep it a local computation. It's not because you need it.
Thank you.
Okay, well, I think that we're now going to go into our lunch break and reconvene at 14:20, 2:20 in the afternoon. So let's thank all the speakers once more, and then go have lunch.